In our next example, we illustrate how to correctly build expressions which are lambdas and for alls at the metaprogramming level. Okay. If one does this in a naive way, using just expression.forall and expression.lambda, the Lean's hygiene is likely to cause you to have errors because hygiene prevents various constructions. Now you could try to block hygiene, there are methods that let you do it, but the hygiene is a feature, not a bug. So the better way of doing it, and the easier way anyway, is to use these very nice monadic methods that let you construct expressions which are of the form lambdas and for alls, and also let expressions correctly. Okay. What we'll do to illustrate this is we will construct a negation which is a little smarter than just putting not in front of each expression. Okay. One could be even smarter at production level, and this would be useful. For example, if you have a AI generated conjecture and you want to prove it, at the same time you want to try to disprove it as well, because the conjecture could well be false. So it's nice to have a smarter form of negation. But here we will only negate using the well-known mathematical formulae. For all x in alpha p of x, if I negate that, you get there exists x such that not p of x. And conversely, if you take not of there exists x px, you get for all x. I'm sorry, there's a not missing here, slash not px. Okay, so these are the formulae that we'll use. We'll match on these. It is fairly complex, so I'll split this into 3 videos, a middle one for just one case and the first and the third for the big cases. Okay, so we're going to not write a tactic here. We're going to instead write an elaborator which will be used to test and explain and give examples of how these work. Okay. So we'll come to exists. We're going to have to turn things into exists. So it's worth noting exists has only one explicit parameter, which is a type field, type family. Given exists, if say alpha is natural number, they exist a natural number with some property. Well, you just have to give the function from natural numbers to that property. So in this case, what we would have to do is give a lambda from x to not px and build it based on that. Okay. In the third video, we will match the other way with exists. But for now, we want to give it that correct parameter. Okay. So let's go step by step. Let's go first with the most naive negation. Okay. So suppose we negate e colon expression. I am going to return a meta m expression. Okay. The most naive expression is a way to do this is to just take makeup m and not and give it just one parameter, which is the expression e itself. Okay. Now this is very simple, but it lets us illustrate our elaborator to look at examples. So what we'll do is we'll create a new syntax for terms, and this is given a term t, which we secretly know is a type, in fact a proposition, and we want to negate it. I return a term, not a tactic. So this means that I have to give it an expression representing the term. Okay. And the expression representing the term, well, first of all, this is syntax for a term. I have to get an expression representing t itself before getting an expression representing its negation. So let's take p to be elab type of t. This is a refinement of elab term, giving Lean information that we expect a type. Lean is not strict about it, but the information is helpful. Okay, and then what I have to do is return the negation, negate p. Okay, let's see what happened in our example. So our example was for all n colon nat, n is not n plus 1. And this just became not of that expression. Or a slightly longer expression, we have for all n is not, n goes to 0 implies n is not n plus 1. Okay, so let's put these aside for the moment because we're going to work with negation and try to refine it. Our first obvious refinement is we're going to match e with nothing. So let's match e with, or rather match it with everything. We give it to this. I just put this in because it's our default case. This will not change our examples, so let's not bother to do it. Now our first main case, which is an expression of the for all e. Well, what are the parameters? There's the name, there's the domain, there's the body, and the binder info. Binder info is telling you whether things are explicit or implicit or not. Okay, let's put a sorry here and just discuss what we have to do. What we have to do is we want to create an exist type, and we want to create an exist type, as I said, with a lambda, and that lambda is going to be the negation of p of x, or more precisely it's going to be lambda x maps to not p of x. Okay, so the nice monadic way of doing it is we work within a local declaration. So let me type the syntax up and we will see what this is supposed to mean. Roughly, when you want, if we have already in negation we had e is expression, so on the right hand side we had a local declaration e. So what this does is it introduces the local declaration and then you continue with the local declaration. So we lit local declaration. Okay. So this is like introducing a variable. We have to give it its name. Okay. The second parameter is the binder info, then the domain. Okay. And then with this we continue, okay, with function of x. Well, this was the result. I don't want this to be the final result. What I want to do is construct a function, let neg function, which is supposed to be here. Okay, I'm sorry, be sorry, and then we put a sorry here. Okay, it has problem inferring the type, so let's just put it as the body for the moment, just to tell it what the type is. There's no body here. I'm sorry, this is not, yeah, body is expression. Oh, sorry, it's a pure body. Okay, we wanted to return something monadic, which was a pure body. We don't want to return the body, of course, we want to negate the body. But first of all, the body in this example would be px. Okay, we have been given this expression x, but internally the body is given by p of the first bound variable. We use De Bruijn indexing and have the first bound variable. So what we want to do is fill that in with x. So we'll say the correct body here is what we call the old body. In fact, this is not monadic. Body dot body dot instantiate 1 of x. Okay, let's give it a do here to tell it that we're going to be using our fancy notation inside here. So this simply fills into the body for the first De Bruijn index, that is De Bruijn index 0, which is the way corresponding to the variable x here. Okay, so this x is a variable which has been created and filled in. But we don't want the body, we want the negation of the body, but not really. So let's say let negation of the body is negate the body. Okay, at this point Lean is going to complain it doesn't know that it terminates. With metaprogramming, we're anyway usually not going to prove termination. We have to be careful. So we'll make it a partial function. So the negation of the body, we negate the body. And but this is not what we wanted to return. We wanted to return a lambda, which will take alpha x of the type alpha. We already have that x here of the type alpha is the domain, to not px, which is the negation of the body. Again, you could try to make a lambda expression, but that would be wrong. What you have to do is use a monadic method, which is called make lambda fvars. Give it the free variables, which is x here, and give it what we want, neg body. Okay. So now what we have done, recall, is inside this with local declaration, we have a local declaration. That is, we are creating something like a lambda or introducing a variable. Okay. We are filling in x into the body, so that filling into the place where there was a De Bruijn index 0, which is the first variable, and negating the corresponding body after filling it in, making the lambda. So this is the function which takes x to not p of x, and what we want to return is make append exists and this is a curious problem. Let me go back and have a sorry here to just check my syntax. So make app m, yeah, this has the wrong type. I'm happy with that because it's expected to have the wrong type. Let's give it the name. We want to make it an exists, and we have the parameters with exists, and that's just the neg function. Okay, let's see what progress we have made. We have look at negate for all, and we created an exists, and we changed the n is not equal to n plus 1 to not n is not equal to n plus 1. The way we did that is we created a lambda function which maps n to not n into n plus 1, and then applied the exists type to it. Okay. So far so good. There is one weird twist here which we'll deal with in the second variable, because remember in the second video, sorry, which is that remember that arrows are also for alls. They just use an anonymous variable, and the right hand side does not depend on the variable. So that will match our pattern and give a slightly weird result. So this gets negated to there exists n, okay, and there exists a, and if we hover on this, you'll see a is a proof that n is greater than 0. So there exists a, and there is a proof that n is not greater than 0, such that not n is not n plus 1. What we really want to say is there exists n such that n is greater than 0 and n is not n plus 1. So we'll handle that special case in the second video in this series.